My name is Christopher Nuland. I'm a technical marketing manager for AI at Red Hat. My job specifically over the last few years has been around OpenShift AI and how different tools are being developed for developers within the OpenShift AI ecosystem. So today is a fun example. I always like to try to find interesting ways to bridge the gap between technology and nostalgia. And this project I'll be showing, I'm going to kind of show you the end so you know what we're working towards. What we're showing today, ultimately, is going to be an AI playing the 1990s arcade game Double Dragon, and kind of how I built that out, what are some of the services I used, how did I program that AI, and then we'll go through some of the results that I had from that AI training. So a couple of fun stories about this. First, something I have to tell you, I was creating this session, and Red Hat Legal found out about it. And so I had an email from them, and they're like, Mr. Nuland, like we need to make sure that we understand what's actually happening here. Basically, where did you get this? I do own this game, just so that everyone knows. I own the game. I pulled the game from the cartridge and created the ROM instance that I'm using to train, just so that we all know that I didn't go into any nefarious website on the internet to find this instance. I will be playing the Game Boy game today. So the Game Boy game I chose because it uses the least amount of RAM and processing power, which means more instances that I can have up and running. So that was a lot easier than using the traditional arcade version or any of the later versions on like the Super Nintendo or Sega Genesis. Second thing I wanted to mention, this project is actually why I have my current job. One of our vice presidents actually is a big fan of like arcade games. And he was, for some reason, going through my GitHub and actually found this project. And he was so interested on it, it came up in an interview, and then ultimately he put me into the position I'm in now because of what I'm actually about to show you. So playing video games can actually help your career. With that, let me go ahead and show you the end result so you know really what we're working towards here. What you're going to see here is a collage of many different instances of the game running. These are all running on parallel. Right now we have an end state. It's going to reset here in a second, and you'll see all the other states going here. So what you're seeing here is over 60 instances of the game running at the same time, and an AI actually playing through it. So we have here quite a few different sessions. In this case, we are all playing on the first level. Most of it is failing, but we'll focus on a couple key areas here. For example, the few that just get stuck. Here's an instance, though, where this is mid-training, where it's actually started to understand a little bit more of the game. You'll find, and we'll talk a little bit more about this, but ideally, it wants to actually be using its elbow. So it wants to do exactly what it's doing here, get in the corner, and then use its elbow to actually attack any oncoming NPCs from the back. So we'll talk a little bit about how we got to this point through some examples. it's meant for, and what it first came out of, was distributed systems focused on high performant algorithms, things like weather simulations, not necessarily even AI. Actually, most of Ray was done more from like a statistical standpoint or mathematical, more of a simulation standpoint. Recently, we've found that Ray is very suited too for AI workloads, especially when we start talking about Kubernetes and how we want to distribute AI across different nodes and different computes. So I'm actually running this within Kubernetes. And it's as simple as what you're seeing here. I just define this cluster. I say where I want the instances to be deployed. In this case, I have a namespace set aside with different nodes. We'll see that here shortly. I set the amount of CPUs I need per instance. I set the type of GPU that I want. And then the Kubernetes instance will then manage all the scheduling from this point. This is, when I first started this project, I was just doing it on a laptop. And what took me 100 hours to do, I was able to replicate the same point, or roughly the same checkpoint, what we call in machine learning. I was able to achieve that within 8 hours of running within this Kubernetes instance. So that just shows you the difference between running in a traditional laptop versus actually running in an industrial, enterprise-grade Kubernetes cluster. So this is where there's still a lot of improvement that we're seeing in the field of AI. A lot of data scientists are still just not comfortable working in this type of realm. They're very used to using single servers or their own laptops. And this is where we're actually seeing a lot of advancement right now, where we can actually improve on the speed it takes to actually run some of these AI simulations. And ultimately, that's what this project is to show, is that being able to distribute these types of workloads has a significant advantage over just running it within a single node. So I'll continue by one to kind of outline what kind of infrastructure we're working with here. And I can actually show you what that looks like. Go to pods. So here I have 3 instances running. The top is the coordinator. So these 3 are all dedicated to their own nodes. So I have each of these servers are running on one individual node, in this case, with a dedicated GPU. Each one of those servers can run about 30 instances of the game. I've scaled this up before to up to 8, and that very expensive, but really nice results too. That's where I actually got the 8 hours from, when I was able to scale up. So I'll dive a little bit more into kind of the nuts and bolts of the AI itself, but I wanted to give you kind of a footprint of what we're working with here from an infrastructure standpoint. So I'm doing this all from what's called a Jupyter notebook. This is basically an IDE running within a web portal. And it allows me to get all the information I need for coordinating all the instances of the game that's running. So here it's just as easy as saying, I want the cluster to come up. I want it to be waiting to be ready. And then it'll give me all the information that the cluster then is active and where that cluster is available to run from. So from a research standpoint, this is very informative, especially for a data scientist or AI engineer. It allows a lot of that coordination of their simulations and AI workloads very easily from one central location. So I'm gonna sit down a little bit because we got a few things of code to kind of run through here. But at that point, I then actually submit the job, and that's where we can kind of go into some of the nuts and bolts here. I have a Minio instance, which I'll show you here in a moment. That's collecting both the checkpoints for the AI, and it's also what's saving all of the videos that you saw earlier. At that point, I can easily submit the job. You can see here I already submitted one, excuse me, about an hour ago. And I can go ahead and show you what that looks like here under the Ray dashboard. So I just had one finish here recently. Instance 9 there at the bottom, that was the one I scaled out a few weeks ago. So that one succeeded. That took 4 hours. When I ran that on my laptop, it would take roughly about 3 days when not running within a distributed type of configuration. And then I ran one recently with the 3 nodes that you saw up already, and that ran and actually succeeded within less than 20 minutes. So kind of giving you an idea of how we can then manage those. Let me go ahead and jump in and show you what the results look like from the game run, and then we'll look at a few instances of the game running as well, so you can get a better idea of what was happening in that collage of videos. I'll go ahead and jump into the logs here. What I love about using tools like Kubernetes here is that when I'm actually doing this locally on my laptop, it's very hard to manage all the different logs and really filter out all the noise versus really critical information. When I'm using Kubernetes, there's a lot of ways that I can then work with the different types of filters and have all instances kind of feeding into one place. And I'll show you what that information, at least what I'm seeing, looks like here. So if we get past all this, this is kind of the meat of it right here. What's really important to me is the amount of steps that the AI has taken. So each step would be basically one tick in the game, like one instance, one control within the game. So the one time that you've actually clicked some type of button. And here, it also tells me the action it took. So this probably doesn't mean anything to you, but like action 4, I think, is mapped to like the up D-pad on the Game Boy. And then I think action 7, for example, is punch. So all of these are then mapped to the particular action that the AI is running. So I have this feeding about every 100 actions just to get an idea of where each instance is. And then what's most important to me too is the amount of points, because it gives me roughly an idea where it is in the level. And then the amount of lives. Has it actually died a few times? A lot of times if the points are low, the lives are high, and the steps are high, that's an indication for me that it's gotten stuck, and I could probably end it early without actually having to look at any of the video information. So from here, I'll talk a little bit about more of the experimentation side. When I was working with this, I've chosen an AI model called, well, it's part of what's called reinforcement learning. So reinforcement learning now is kind of a hot topic because DeepSeek is using reinforcement learning for the training of their AI models. But before LLMs, it was a very popular predictive AI tool as well. And I'll dive in and kind of give you an idea of what some of that looks like. So when you're working with predictive AI, you have things called rewards. I don't have it mapped out here. Actually, here's a good one. So when it's detected that the player has died, I take 50 points away from the AI model. This is just telling the AI model, hey, we don't want you to die often. Now, that doesn't mean, if the consequence, though, is if we increase that too much, then it won't do anything. The death penalty will be too great compared to the reward of exploration or scoring. So it's a balancing act. It's constantly tweaking these parameters to try to get the best results. If you don't have any death consequence, though, it then goes all Rambo on you and won't make it too far through the level because it's not trying to conserve its own health and its life. So that is a key part of how we reward the AI. And like I said, I'll give you an example of some of that here shortly of how the different configurations look. We'll look at some of the videos. We do also have the positioning. So if there's anything you get from this talk, I would say this is like one or two of the critical parts here. When doing this experimentation, I had put emphasis more on scoring. And when I put emphasis on scoring, I actually didn't get very far through the level. Can anyone guess what's more important than scoring? Moving forward. Moving forward. So what we actually find is that positioning is the most important. And to surprise everyone, this is not just a thing for Double Dragon. We're finding this is the case in pretty much every video game that has some element of exploration or movement, that a lot of times the score does not have much impact into the game. It's actually the ability of exploration that has the most impact into the success of the model actually running the game. So once I started actually implementing the positioning into this, we actually started having much larger success within the model. There are actually iterations where I actually turned off scoring and it ran just as well as the positioning. I do have a little bit of scoring in there because I found if in cases where there's like a boss fight, there is advantage to scoring because so much scoring happens within that zone. There has to be some initiative for it to actually want to continue to fight rather than try to survive and try to position itself more. So it's a balancing act. But what we're finding is there's some research papers out on this effect right now that are really focused on this from a broader standpoint. So it's not just video games. This also comes up in like robotics. How do robotics like traverse area and territory? It's more about the exploration and the positioning and less about the actual actions that it can take at that point. So a real world benefit here of exploration is more important than the points itself. So let's talk about a little bit how I get this information, because this is what people always find very interesting here. So I'm using an emulator called PyBoy. The nice thing about PyBoy is that it runs in Python, which makes it very easy to run within these types of experimentations. And it also allows me to access the individual memory points to get things like health, lives, a variety of information, like the X and Y positioning. What's interesting here is that this information wasn't available to me. I was looking at, does anyone remember GameFAQs? Like the very old game forum from like 20 years ago? Okay, wrong crowd. But there was this forum from when I was a kid, and it's still up today, and I was looking through some of the old forum information to try to find information about this memory. And I was actually able to find a little bit, but I eventually actually had to bring up an emulator myself and pretty much hack the game to find all of these different memory points. So there's another community. So I came up with these particular memory points, but there's a few other communities that are doing similar things with like Pokemon, Mario, Kirby. And it's really become almost like a speed run type of thing where we're trying to develop different types of AI to see how fast or how far we can beat these certain video games. And the critical part here is being able to get this information. Obviously, some people are using OCR, so using like more of a visual type of approach, but that's not as effective as actually running actually having this information straight from the emulator itself. The video you saw earlier is just doing one save point, which is this one right here. It's the beginning. What ends up happening if we just use that one save point, though, is that it ends up getting overtrained on that particular part of the game. Ideally, what we want to do is actually run random instances, parts of the game, so that the AI gets a feel for the different types of levels. The biggest example for this would be the first level is on an x-axis. The second level is actually on a y-axis. It's actually going up and down and doing the exploration from different types of ladders as it explores. If you were to just train the game on the first level and then apply it to the second level, it's just going to run straight off the level. And you'll see some examples of this as I show a few of the videos for this too. So all the information for each instance of this running then saves into a Minio bucket. If you're not familiar, Minio is an S3 storage bucket. It can run on things like Kubernetes really easily. And this is where I save the state. This allows me to kind of, it's a snapshot, you could say, of the AI model. And then the cool part here is in the videos. I can actually see where individual training sessions are running. And let's see, I'm just gonna pick one randomly. We'll see if it downloads. If it doesn't, I have a few already downloaded. Let's bring this up. So this is the first level. This is actually looks like it's done pretty well because it's clearing through this first part. And here's an example of what I was talking about earlier. Typically what this means is that it's trying to anticipate that something that's not going to happen. It thinks that there should be more NPCs showing up than are actually there. And this is an example of it wanting to survive more than to progress. So when I see these types of actions, it's an indication to me that I actually need to increase the exploration amount and encourage it by increasing the points as it traverses through the game more. Let's see if it does anything else. It may, no, it does eventually. See here that it's, yeah. So this is pretty good. It actually got through a decent part of the first level. Let's see if we can find one that has maybe a different level to it. I'm just going to pick one by random. These later ones typically are a little bit better as they've been trained longer. The same one. Yeah. Let's try this one as well. Let's just play it from here. So this is an example of it running on the second level. Let's see if we can see it jump off. No. So this is an example where it's trying on the second level. There's ladders here that it needs to eventually get to that it's just not going to get to. And all that's happening based off of the reward system and how we adjust it from there. So let me go ahead and show you the last session that actually does succeed. I have a video of that here. So when I was training for this, I had about 3,000 sessions. And of the 3,000 sessions, I had just this one that actually finished the first level. So just to give you an idea of the complexity of this, and I was running these experiments for about 6 months. So it took a while to get to this point. They just beat Pokemon Blue. That was a competition between, I think, about 20 different people working on it. And even then, they weren't using one single AI approach. There was multiple agents being used to actually accomplish that. And that was a team of an open source group working for about 2 years on that as well. So just to give you an idea of really this community that has formed and some of the complexities to it and why one person can take 6 months to actually accomplish. But here's an example of it beating the game. You'll see the critical thing here is the back elbow, like I told you. I shared this video with a speedrunner last year, and the speedrunner was really fascinated because the AI had actually developed many of the same techniques that the speedrunners use for this particular game, specifically the elbow and how it positions itself within the game as well. So here it's anticipating that door opening pretty well, and as you can see, it did a really good job. This boss was very difficult. This is where it usually loses, but it then developed a kind of a pivoting. And you'll see here the staircase where it has a lot of challenges. It does eventually get up, but this level is then ultimately where it failed for me. I got to the point where it got to the end of that second level, but I haven't been able to actually overcome the boss there from this point. So kind of putting this all together, we have the infrastructure component with Kubernetes using Kubernetes to be able to manage the different instances, in this case, the Game Boy emulation, and being able to see all the information in one place. For me especially, it made me able to move faster developing this and competing with the AI community, as I'm getting a lot more information from this a lot faster than if I was running it on a single server. I was able then to adjust the reinforcement learning to be able to actually beat that first level by focusing more on positioning than scoring, ultimately. And then right now, long term, I'm looking at a couple of more games that I'll be doing these types of demos with. My team is also working on trying to play Pokemon using an LLM as well, all run within Kubernetes. So that's something we're working on towards the end of the year. This is all predictive AI, so more of your traditional AI, but we're starting to move more into a generative AI approach to actually solve some of these, what we would consider more complex spatial type of challenges that you see in old school arcade and traditional video games. So with that, does anyone have any questions?
Thanks for the presentation. This was really cool. So did I get it right that your model doesn't actually look at the screen?
No, it does not.
So basically, it learns how to go by heart, blind.
It doesn't go. So the question here was, is the AI completely blind, and is it not actually looking at the entire screen? It doesn't look at the screen from a traditional sense, so it's not like we're taking snapshots and images of the screen. It does have access to the memory of the array, the matrix array that holds the screen information. So like when you're playing your Game Boy, there's a dot matrix there for the grayscale. It has access to that information, but I take that information and compress it. So it gets a much smaller form. When it actually is looking at the information, it's just a bunch of blobs moving, but it does have some information being passed to it on the objects. It's not strictly the words. Yes, correct. Yep.
Okay, and the second question. Do I get it right? The emulator is not running in real time. You're stepping it through when learning, or is it running in real time?
It's running real time.
Sorry?
It's running the emulator.
But the emulator is running at the real time speed.
No. I have it running much, much faster, correct.
You are running much, much faster.
Yes.
Okay.
It's at the maximum amount that the emulator offers, which is about times 50 of what a normal play would be for the Game Boy.
And all the processing, the model training is able to keep up with it?
Yes, correct. And that would be challenging if it was just, sorry. The question was, can you repeat it so I can get?
So are you running the model, like the emulator in real time?
Yes, so are we running the emulator in real time? So would it be the same as like you playing the Game Boy? And the answer to that question is no, we're running it about 50 times faster than what a traditional Game Boy would run at. Any other questions? The question in the back?
You tried to automatically link the reward function, for example, through some parameter search?
Yes. So the question is, have we done some, in AI, there are ways that we could automatically adjust some of the parameters. As I mentioned, I was doing it all manually. The answer is absolutely yes. I could do that. And if I were to continue this, I would. For the team that beat Pokemon Blue, that's exactly what they did. They did auto parameter tuning. I personally like to do my approach manually first so that I get a better understanding of what affects what. Like I have a better understanding when I'm actually manually adjusting it. And then I think now if I were to do this more competitively, I'm waiting for someone else to try this. So I put my code out there and I've reached out to some people. So if there was a team that actually started putting this together, I would absolutely start doing that if I was doing this more competitively where I would want to get the best results. But for me personally, I wanted to adjust the parameters manually to get a better idea of what affects what. Any other questions? Question there? Yeah. So I think this is an interesting question. I'll repeat it in a second. Okay, I'm really good. I got it exactly right. That is roughly what it's saying. When the question here was, what is it visually seeing? It's kind of like the first question, but what does the AI model information have when it's making the decisions? It has a matrix that looks like this. In this case, can anyone guess what I'm doing here, by the way? Is there any guess here? Okay. These are actually 3 frames from the game stacked on each other. The middle frame is the frame that is currently happening. That is the top frame is the previous frame, and the bottom frame is the next frame. So instead of sending 1 frame at a time, I'm actually sending it 3 frames over the course of 3 iterations. And this helps the AI make better comparison. Like it has more information here that it can make decisions off of than me just sending 1 frame at a time. But this has been compressed because if I sent the actual full matrix to it, it would just overcomplicate it. It would just be too much information for it to work off of. So this is the ideal type of information to send to it to make the best choices. Question in the back? Yeah, so the next frame, so that's a good question. Think of it as, this is more in terms of how the Game Boy sends information back to, so the question there was, what do I mean by that next frame? Just think about it as, this is what's currently being sent to the screen. This is, the middle is the current action that's being processed by the AI model. And the top one is the previous action that was handled by the AI model. It's now running through the bottom one. It has no information on that quite yet. It does have information on what was just currently processed. So it's more about what the AI model is processing, not about what is visually being on the screen. So it's already processed the top. It's currently processing the bottom. It hasn't processed this one yet. Any other questions? Out of time? All right. Thank you so much. This is a project. Thank you. This project is available on my GitHub. You can come by, reach out to me on LinkedIn, or come by if you want more information. I'm also looking for information on other games to do similar things, either with predictive AI or LLMs. Thank you for your time.